recording will be posted today or early tomorrow and will be available until midnight Eastern Standard Time, Friday, November 26th. Okay, so start off with some announcements. So Georgian College Fitness Center is open Monday to Friday from 3 to 8 p.m., so you can go in person. Now, you must be enrolled in courses at the college. You need to present your one card to enter, and you need to book a time to use the facility. I believe they're taking 25 people per hour. There are details on a Blackboard on the program, the Fitness and Health Promotion Program Blackboard site. There was an announcement a couple of weeks ago when they first opened up that has a link to get your one card and a link to details from athletics. We really encourage students to adopt a regimented exercise routine, because in second semester you will have courses such as applied anatomy, personal training, fitness appraisal and testing, where you will be required to demonstrate your proficiency at movement and at performing set exercises or demonstrating them or explaining them. And the faculty and staff do notice a large difference between students who have or do perform a regular exercise routine and those who don't. So something as simple as, can you place an appropriate amount of weight on this bar with safety clips that keep the weights on the bar? Students who have exercised, that's no problem. It's second nature. Students who don't, it's a new task for them. And so it takes away from, for lack of a better phrase, your cognitive real estate to perform the actual tests that you're performing. So it is encouraged that students participate in that. Now, the Georgian Dining Room and Bun on the Run is open. It is only open to students and college staff. So pre-COVID, it was open to community members, and as of right now, it is not, although that may change in the wintertime. For the Georgian Dining Room, it is the E building, room 100. They are sit-down meals, and they are open Monday to Friday, and you need to show up at 12 o'clock, and you should really make a reservation. If you show up at 1 o'clock, it's too late. So you need to show up at 12 o'clock, make a reservation, and it'll probably take you anywhere from 60 to 90 minutes. It is a sit-down service. For students, it is basically, you can get a 3-course meal for $8 Canadian. So that's appetizer, entree, and dessert. And they do offer vegan and vegetarian options. They are also open on Wednesdays for dinner time, and you need to show up at 6 o'clock for that. Bun on the Run is also in the E building in room 109, and that is food to go. And they are open Wednesdays and Thursdays, and you show up anytime between 11:30 a.m. and 1 p.m. And basically you just go in, request the food that you want. They'll typically have 4 or 5 menu items, pay for it, and you can take it and go and eat somewhere else on campus or at home if you wish. As always, we have another quiz coming out this Friday at 4 p.m. Eastern Standard Time, and it will be available until 4 p.m. Eastern Standard Time on Friday, December 17th. Normal format, 20 questions. Most of them will be multiple choice. You may get some true false, 30 minutes to complete, and you have unlimited attempts. As a reminder, all of the quizzes together account for 10% of your final grade. And I did a quick scan recently, and there are still some students who haven't even done one quiz or only did one quiz. So even if it's pre-midterm, do the quizzes, because you can do each quiz 3 or 4 times and get 80%, and this way you're getting 8 out of 10, and that can substantially alter your score. Also, students who perform better on the quizzes, so students who attempt the quizzes 3 or 4 times each and get the 80% or above, perform substantially better on the final exam than those who do not. And as an added bonus for this week, there is a video on the cardiovascular system and exercise. Now, this is from Dr. Jamie Burr, who teaches at the University of Guelph, just down the highway from us. It's posted in the course information on Blackboard, and some of the questions from the quiz will be from this video, which means that some of the questions on the final exam could be from this video. And so as a snapshot of where we are in the semester, looking at weeks 10, 11, 12, 13, 14, we are in a 14-week semester right now. We are here November 22nd to 26th. You had a research paper due about 5 minutes ago, and you had quiz 9 last week. Now we're having quiz 10 coming up. And then moving forward, we will talk about respiratory physiology. Next week, we will not have any set labs. It'll just be the lecture. And then the week after that, the week of December 6th. So class on December 7th will have exam review, and then December 14th will be your final exam, and that will be the end of the semester. So it's gone by quick. So today we're going to talk about cardiovascular physiology. This is in chapter 18 of your textbook, pages 671 to 702. Just to give you a background, when I was in grad school, I worked with heart transplant patients, heart failure patients, and other heart patients, so patients with various heart diseases. So this is a topic that's near and dear to my heart, and I'm familiar with the basics, at the very least, and some of the more cutting edge stuff. So the heart, there will be overlap between this course and anatomy because we do need to address what the cardiovascular system is, how it works, but we are going to go more into the microscopic level of things as opposed to the macroscopic level, things you can see without the aid of a microscope. So the heart anatomy, as we mentioned in the lab, when we're looking at the heart, our left side is actually the right side of the heart, and the right side is actually the left side of the heart. So the heart consists of 4 chambers. You have 2 atria, right and left, and you have 2 ventricles, right and left. Okay, so we will start with some of our annotation. But it's a transport system. So really it's 2 side by side pumps. Okay, the right side receives oxygen or blood from the body, and then pumps blood to the lungs to get rid of CO2, carbon dioxide, and to pick up oxygen via the pulmonary circuit. So the pulmonary circuit is basically the circuit from the heart to the lungs back to the heart. The left side receives oxygen-rich blood from the lungs and pumps blood to the body via the systemic circuit. And that's basically, that's like the basics of it, okay? So your atria are your receiving chambers of the heart, and the ventricles are your pumping chambers of the heart. So the right atrium will receive from the systemic circuit. So we can see in this diagram here that we have the systemic circuit is basically for the body. So the right atrium will receive blood from the systemic circuit, and then the right ventricle will receive blood from the atria and pump to the lungs, which is your pulmonary circuit. So this pathway is your pulmonary circuit. The left atria receives from the lungs, and then will send to the left ventricle, which will send out to the body to the systemic circuit and goes back. Now, the heart itself as an organ will weigh approximately 1 pound. So if you were to take your hand and form a tight fist, like you're going into a boxing match or a contact sport, that's about the size of your heart. And to give you perspective, we talk about in this program and this course in exercise physiology how with cardiovascular training, the heart actually gets a little bit larger, but not too much larger. So if you had that tight fist and you loosened it up a bit, so it's just a fist, it's not a tight fist, that's the size of an athletic heart. The heart can grow a bit with athletic training. Now, if we were to say, hold both your hands like this, as if you're holding a cantaloupe melon, that would be an enlarged, diseased heart. The heart with certain diseases can get so big that it actually becomes dysfunctional. It doesn't pump blood properly, and then you may get into multiple issues with that. Okay, so the layers of heart, you have multiple layers of the heart. We have the epicardium, which is technically a visceral layer of serous Oh, there you go. Pericardium. It's like connective tissue. You have the myocardium, which is circular or spiral bundles of contractile cardiac muscle cells. So this is the functional, like the operational part, because the heart is a pump. And so when these muscles contract, and remember, the only thing a muscle can do is shorten, a muscle fiber can do is shorten. When these muscle fibers shorten, it makes the inside of the heart smaller and pumps out that blood. And then we have cardiac skeleton, which is a criss-crossing, interlacing layer of connective tissue. Okay? And so the cardiac skeleton is what will anchor cardiac muscle fibers. Right? When those muscle fibers contract, they need to be contracting and pulling something. And so they pull on the cardiac skeleton. The cardiac skeleton will support the great vessels and valves. Now you will have these big blood vessels in the heart itself that will feed the heart itself and drain blood from the heart itself, because the heart is a muscle, it needs blood. So the cardiac skeleton will help support those vessels, and also the valves. So you have the semilunar valves, the pulmonary and aortic semilunar valves, and you have the tricuspid valve and the bicuspid valve. So the cardiac skeleton will support those, and also it will limit the spread of action potentials to specific paths. Because heart tissue, the myocardium, is excitable, we want those signals going in a certain direction. And if they don't, we have serious health issues. So the heart's a double pump, and we have equal amounts of blood, which will be pumped through the pulmonary circuit, right, to the lungs and back, and through the systemic circuit to the body and back. Now, the pulmonary circuit is low pressure. So where's our annotation? So pulmonary is low pressure, okay, and it's short, like it's a short distance. Whereas a systemic circuit is long, high pressure, okay? And the anatomy of the ventricles will reflect that. So even if you were to look here, the left ventricle has thicker walls and it's actually a bigger chamber than the right ventricle. Now, what this shows here also is the flow of blood through the various structures of the heart. So we have the body, or systemic capillaries, goes back through the inferior vena cava and the superior vena cava to the right atria, goes past your tricuspid valve to your right ventricle, goes past the pulmonary semilunar valve to the pulmonary trunk to the lungs, right? And then here at the lungs goes back via the pulmonary veins to the left atria, back past the bicuspid valve to the left ventricle, and out the left ventricle past the aortic semilunar valve to the aorta. So just as a tip for anatomy, I don't know if you have cardiac anatomy on your midterm or your final, but if you want to learn the structures of the heart, be able to be able to label in order the structures of the heart as blood passes through them. So you have and I'm going to use short forms, you have inferior vena cava and the superior vena cava, which goes then to the right atria, which goes past your tricuspid valve, which goes to the right ventricle. And in there, you're going to have the papillary muscles and the chordae tendineae. And from the right ventricle goes past your pulmonary semilunar valve, and from there goes the pulmonary trunk, and so forth and so on. So if you can label that from memory, then you have a pretty good opportunity that you know the major structures of the heart. There's a third circulation, and that is the coronary circulation. So we talked about, systemic, which is basically to the body. And we talked about pulmonary, which is to the lungs. And then number 3 would be coronary, because the muscles of the heart themselves require oxygen and nutrients, because these are muscles that are contracting all day long, 24/7 hours a day, 24 hours a day, 7 days a week. So in terms of the coronary circulation is basically functional supply of blood to the heart, right? Shortest circulation in the body, and it's delivered when the heart is relaxed. So when the heart contracts, the blood's not being delivered, but when it relaxes, the pressure is off those vessels and the blood can get through those vessels. And the LV, which stands for left ventricle, receives most of the coronary blood. Okay. So in terms of coronary arteries, both right and left arise from the aorta base and supply arterial blood to the heart. And so we can see we're looking at the anterior side of the heart on the left-hand side and the right-hand side here, but you can see, if you look, that you have the outline of the aorta, which goes behind the pulmonary trunk. We have rising out of that the left coronary artery and the right coronary artery. So right after the aortic semilunar valve, you have the coronary arteries come off. Now they will basically encircle the heart and they'll branch off, and the branching can vary with certain individuals. But the heart receives about 1/20th of the body's blood supply. So for such a small organ, right, it weighs maybe 450 grams or about a pound. And so let's say a person could weigh anywhere from 50 kilograms to 100 kilograms. It receives basically 5%. Like it's disproportionate for a size. It receives a lot more blood for a size than other organs do. In terms of the coronary veins, they basically collect blood from the capillary beds. So it goes through the coronary arteries and we get branching off, and then that blood has to be collected via the cardiac veins to be put back into the right atria. So when we talk about a heart attack, what we mean by a heart attack is that you may have a blockage of, say, this artery here due to plaque. And if you get a blockage of this artery, then any part of the heart which is fed from that point on will be starved for blood and be starved for oxygen, nutrients, and could either be stunned or die off. So when you have a heart attack, the priority is get that blockage cleared. And whether that is via what we call clot buster drugs or aspirin or something like that, or if we have to put a stent, or if we do a bypass right away, that's what a heart attack is. And the technical name for a heart attack is myocardial infarction. So now we're going to go into the microscopic anatomy. So this, you may have covered this in anatomy, but this will probably be towards the end of what we're going to cover. That's the same as in anatomy. So cardiac muscle cells. They are striated, short, branch, they're fat, and they're interconnected. So we can see that they branch off here and that they're all connected with each other. And here we see through a microscope the different cardiac muscle cells. Okay, there's one central nucleus, maybe two, probably not. You have numerous large mitochondria. Right, these take up anywhere from 25 to 35, 35% of cell volume. And these give fatigue resistance. And we want fatigue resistance because the heart is pumping 24 hours a day, 7 days a week. The rest of the volume is made up of sarcomeres, and the T tubules are wider but less numerous. So we have bigger T tubules compared to skeletal muscle, but not as many. And the sarcoplasmic reticulum is simpler than in skeletal muscle cells. And there are no triads. So those are basic characteristics of cardiac muscle cells. Now you have these things called intercalated discs, which are connecting junctions between cardiac cells that contain the following. First off, desmosomes. Now desmosomes hold cells together and they prevent cells from separating during contraction. And you can see that on the cartoon picture to the immediate left. Okay, you also have gap junctions, and these allow ions to pass between cells and basically electrically couple, adjacent cells. And this makes sense because you don't want all of the cells just contracting wiggly piggly. What I mean by that is you don't want you want a uniform contraction of the cells. So this permits functional syncytium, which is a single coordinated unit that they'll all be synchronized so that it contracts as one and you actually get this pumping action. The intercellular space has connective tissue matrix, which is your endomysium. It contains numerous capillaries, which makes sense. You want a large blood supply to the heart, and it connects cardiac muscle to cardiac skeleton. and it gives cells something to pull against. So the whole idea is that this endomysium, you have the supply network for the blood to bring in basically nutrients and oxygen to remove metabolic waste products. And then also is connecting the muscle to the cardiac skeleton so that when the muscle contracts, it can actually pull against something and not just be empty contractions that do nothing. So, of course, we're going to have a comparison between the structure of skeletal muscle and cardiac muscle. So, with structural skeletal muscle, it's striated, they're long, they're cylindrical, right? Not as branched, and they have multiple nucleus. Cardiac muscle are striated also, so you have these stripes, but they're shorter. They're branched, right? Interconnected, and you have one or maybe two nuclei between the cell. With skeletal muscle, you don't need to have these gap junctions because skeletal muscle cell can contract or not. It doesn't matter necessarily what its neighbors are doing. But with a heart cell, you do have these gap junctions that help the action potential to travel from one cell to the next. So you get more of a uniform contraction. And so the heart contracts and acts as a pump. In terms of contracting as a unit, no. Like with skeletal muscles, individual motor units must be stimulated in order to contract. So it doesn't matter what the neighbor cell is doing necessarily. But with cardiac muscle, yes, you are going to have these gap junctions, so you can get basically a functional syncretism, like a synchronized when we get contraction, so it acts as a pump. We have a number of T-tubules in skeletal muscles, not as many in cardiac cells, but they are wider. The sarcoplasmic reticulum, right, that's your basically bank of calcium, is going to be elaborate. And we have these terminal cisterns, less elaborate, no terminal cisterns in your cardiac tissue. The source of calcium for contraction in the muscle cells and skeletal muscle is the sarcoplasmic reticulum, and that's it. But in cardiac cells, you could get calcium either from the sarcoplasmic reticulum and extracellular fluid. To activate the sliding mechanism for contraction, the calcium binds to troponin in both. There are no pacemaker cells in skeletal muscles, but there are pacemaker cells in cardiac tissue. And this means that there are cells which will contract of their own volition to act as ensuring that the contraction of the heart in total is regular. Tetanus being that sustained isometric contraction. It's possible to do that in skeletal muscles. Your muscles are doing that right now where you're maintaining your posture, but not with the heart cells. And it makes sense. You don't want the heart cells just to do an isometric contraction because then it's not pumping and shortly it'll never pump if it keeps it up. With skeletal muscles, they can be aerobic or anaerobic. Heart muscles are aerobic, and that's it. Now I think I stopped sharing, so I apologize for that. Don't know why that happened. Funny things happen sometimes with the computer. Okay, so moving on. We talked about like the physical characteristics, but you need to understand also how contraction occurs. So we're familiar, hopefully, with the concept we're going to talk about next. We're going to talk about action potentials. Cardiac cells are excitable, just like muscle cells and nervous cells are, and smooth muscle cells. That means that they have a resting membrane potential, which is usually negative, but it can go positive depending on the flow of ions. And so what we see with cardiac muscle cells is we see basically three parts here. We see a pacemaker potential. So it starts at about negative 60 millivolts, but slowly goes up until it reaches a threshold of negative 40, and then really depolarizes, goes just above zero, and then repolarizes all the way back down to negative 60. But then we see a slow pacemaker potential. So the pacemaker potential means it's slow depolarization because both sodium channels are opening, but potassium channels are slow to close. And so the membrane potential is never a flat line. You never have where it's just sticking at negative 60. So in terms of the heart and we've got a lot of notes already on here, so I'm going to probably put up some notes and then take down some notes and put up some more notes. The heart depolarizes and contracts without nervous system stimulation. And we know this. So a good example are heart transplant patients. So let's say for some reason your heart becomes diseased. Maybe you get dilated cardiomyopathy, maybe you had a heart attack, maybe you had a bacterial infection of your heart. It becomes disease and you go into heart failure. The heart cannot pump enough blood to meet the energy requirements of the body. So if you're a heart transplant recipient, what they do is they literally cut open your chest, take out your heart, and put in a donor heart. And even though all the plumbing, all the blood supply is hooked back up, they can never reconnect the nervous system. Once they cut that heart out, they can't get the nervous system to grow into the new heart. And so we know that the heart can contract without nervous system stimulation. And because also if we were to do a biopsy of the heart, which you can do a biopsy of the heart, you go down to the jugular vein and you take a little snippet of heart tissue and it doesn't hurt you. You can live without it. And we put it in a petri dish with nutrients, the heart can contract on its own. We don't have nervous system there. However, the rhythm it's going to get you can be altered by autonomic nervous system. So on its own, the heart will contract at 90 to 100 beats per minute. Average resting heart rate is 72 beats per minute, and it can go as low as the 50s or 40 beats per minute. The parasympathetic nervous system will exert its effect, will have its effect on the heart to bring it down from 90 to 100 to 72 or 60 or 50. If you're lying down or sitting down. If you get up and start walking, the parasympathetic nervous system will withdraw its effect so the heart rate can go back to 90, 100 beats per minute. If you start jogging, the sympathetic nervous system will kick in and activate to get your heart rate up to 140, 150, and then so forth and so on. So it can be altered by the autonomic nervous system. No, just do there. The coordinated heartbeat is a function of, first off, presence of gap junctions, and secondly, intrinsic cardiac conduction system. Okay, so we have these non-contractile cells which initiate and distribute impulses to coordinate depolarization and contraction. So these gap junctions will help because they let the ions go from one cell to the next. However, also this conduction system, right? These tissues don't contract; they're not excitable in that sense. Sorry, they are excitable, but they don't contract. But they distribute the the action potential throughout the heart. And we're going to have to remove some of the writing so we can put some more writing up there. Yay! So the action potential is initiated by pacemaker cells. Cardiac pacemaker cells have unstable resting membrane potentials called pacemaker potentials or pre-potentials. And the three parts are pacemaker potential, depolarization, and repolarization. Okay, so depolarization. So the pacemaker potential here, the potassium channels are closed, but sodium is slowly going in, which causes the inside to become slightly more and more positive. Depolarization at about negative 40 millivolts, calcium channels open, so a large amount of calcium goes in to the rising potential, and then repolarization, the potassium channels open, allowing the potassium channels to go back out, which causes negative. So in terms of the order of events, it all starts with what we call the sinoatrial node up here. Sinoatrial node is basically at the superior part of the right atria, and it will go then to the atrioventricular node. So this sends a signal to the atrioventricular node, which will send it down the atrioventricular bundle and the bundle branches, and then we'll go up the right and the left bundle branches through the subendocardial conducting network, Purkinje fibers. So on this chart, we see basically the different depolarizations at different parts. So we see depolarization of the SA node, which leads to depolarization of the atria, which leads to depolarization of the AV node, which leads to depolarization of the ventricle. And you notice that we have a bit of a pause between depolarization of the atria and the ventricle, and we need that because the atria, the tricuspid bicuspid valve will open to allow blood from the atria to the ventricle, and then the atria will contract to kick that last third of blood through, and then relax, and then the ventricles contracting. If you have the ventricles contracting at the same time as the atria, you get no flow of blood to the lungs or to the body. Everything just stands still. If anything, you might get blood pumped backwards, and that's not what we want. So the SA node, we'll start up here. Sinoatrial node is a pacemaker of the heart, and it is in the right atrial wall, and it depolarizes faster than the rest of the myocardium. And it generates about 75 times per minute. So it's contracting about 75 times per minute. Again, if the heart were just left to its own devices, it would contract at about 100 beats per minute. And the impulse speeds or spreads across the atria to the AV node. So the SA node is going to be, and sorry, node should be NODE, sorry about that. The SA node is the pacemaker of the heart, right? This is what's going to start the generation of the action potential to get the heart contracting. So we're going to need to clear that out because our images are a bit big. My images are a bit big. Okay, so the AV node, atrioventricular node, is in the inferior interatrial wall, and it delays impulse about 0.1 seconds. And this has an inherent rate of 50 times per minute. Okay, So if the SA node was not there, the AV node would be sending contractions out or extra potentials out every 15 minutes. Now, your AV bundle is in the superior interventricular septum, right? The wall. And it's the only electrical connection between atria and ventricles. And there are no gap junctions between the atria and the ventricles. It causes it's the bottleneck because we don't want everything going through without control from the atria to the ventricle. Otherwise, we don't have coordinated contraction of the heart. Right and left bundle branches, okay, are two pathways in the interventricular septum. So in that wall between the right and left ventricle, these are the pathways for the signal to go down and carry impulses to apex of the heart. And the apex is the bottom of the heart. And then the subendocardio conducting network, also called Purkinje fibers, are the complete pathway through interventricular septum into apex and ventricular walls. More elaborate on the left side. Why? Because the left side of the heart is bigger. Needs to pump more blood with more force, and not more blood, but pump with more force, has further distance to go. The AV bundle and subendocardial conducting network to polarize at about 30 times per minute. That is if they were without the AV node. And then ventricle contracts from apex to atria. So if the ventricle were V-shaped, such as my hand, then it would contract from the bottom up. Like it would basically be like this, right? Going from the apex up to pump it up towards the aorta or to the pulmonary trunk. And the whole process from initiation at SA node to complete contraction takes about 0.22 seconds. So it's quick. So really we're talking about the electrical system of the heart. And if you want to bring it down to two simple characteristics or categories, we should say, of issues with the heart, it's either hydraulic, the plumbing, the blood, or it's electrical. Right. And so when we say hydraulic, we'll think about what a myocardial infarction is, a heart attack. A heart attack is when there is a blockage in one of the blood vessels going to a portion of the heart. Well, that's hydraulic, that's blood. With electrical issues, it may be that your heart has fibrillations, or it contracts too fast, or it contracts too slow, or the contractions aren't quite right. You're missing contractions. Well, that's electrical issues. So that's basically what you can boil down issues of the heart with. So if you're going to modify the rhythm of the heart, you have a cardio acceleratory, not acceleratory center, which this sends signals through the sympathetic trunk to increase rate and force of contraction. So when you're exercising, so right now, let's say that you're sitting there and your heart rate is about 60 beats per minute. You get up and start walking, and within 60 seconds, your heart rate's up to 95 beats per minute. And then you start jogging, and your heart rate goes up to 130 beats per minute. And then you start running fast, and your heart rate is now 185 beats per minute. To get more blood to the working tissue, the blood just doesn't contract more per minute, but it contracts with more force. So the cardioacceleratory center will stimulate the SA and AV nodes, heart muscle, and coronary arteries. Now, you also have a cardio inhibitory center, and this is parasympathetic through the vagus nerve to decrease heart rate. And this inhibits the SA and AV nodes through the vagus nerve. So as you're sitting there and your heart rate is below 90 to 100 beats per minute, that's a parasympathetic nervous system exerting its effect on the heart so that it's a lower heart rate. You don't need to have your heart rate going at 100 beats per minute. You don't need to have quite as big force of contraction of the heart. You can sit there and it can be a little bit lower. Now, as we mentioned with heart transplant patients, well, if this system, so when you get a heart transplant, basically these nerves are cut and they have no effect. Well, how does that work then? How does it work that someone who's had a heart transplant could exercise? Well, this is where catecholamines, hormones, fit in, epinephrine and norepinephrine. So when a heart transplant patient starts walking, whereas for a normal person with their native heart, your heart rate would maybe go up within 60 seconds, a heart transplant patient relies on the hormones to take effect. So it may take up to 5 minutes for the hormones to kick in and take effect, and then heart rate goes up. And when they stop exercising, it can take then 5 minutes for the hormones to dissipate and break down, and heart rate comes down. Whereas with you, with someone who has their own heart that they're born with, heart rate maybe comes down in 30 to 60 seconds. Heart transplant patient takes 5 minutes for the heart rate to come down. Okay, so let's give a break right there. We're going to pause our recorder, but we've got to knock this first, and we're going to vote. The heart, the anatomy of the heart, the microanatomy of the heart, and then the basics about the depolarization of the heart. That is how we get action potentials and how we get the heart to start contracting. So we're going to go back to our presentation. And again, if you have questions, put them in the chat. I see that somebody answered somebody else's question in the chat. Sorry, I didn't notice that, but thanks for doing that. Much appreciated. So what we're looking at here is we're looking at membrane potential. So we have negative 90-ish millivolts all the way up to plus 30, and then back down to negative 90. And we have time from 0 to 150 to 300 milliseconds. So the contractile cardiac muscle cells, now to clarify the difference, this was really showing the overall electrical events of the heart. Here we're looking at the contractile tissue. So contractile muscle fibers make up the majority of the heart. Most of the heart is made up of the contractile muscle fibers, and this is what's responsible for the pumping action. Now they are different from skeletal muscle contractions. Skeletal muscle contractions do not have this plateau. So you see that depolarization occurs, it's very quick, but then you have a plateau in repolarization, and then the muscle cell will repolarize. So the blue line represents the action potential. The purple line represents the actual contraction. So depolarization, repolarization occur before you get contraction. So the steps are involved are depolarization. So we have depolarization, we have sodium going into the cells through fast voltage gated sodium channels. And this positive feedback cycle, it basically, when some of the sodium channels open, a lot of the sodium channels open. And this brings the membrane potential up to 30 millivolts. Then at the end of this, those channels are inactivated. At about 30 millivolts, the sodium channels will close and slow calcium channels remain open, which gives you this plateau. So this plateau is caused by these slow calcium channels. So you have still calcium, which has a positive charge, still going in, which keeps the cell depolarized. And then at about 200 milliseconds, the slow calcium channels close, the potassium channels open, and potassium leaves the cell, so you have repolarization. And that's where you get the repolarization right here. Okay, and then the calcium is pumped back into the sarcoplasmic reticulum or into the extracellular space. Now, with the action potential in skeletal muscle will last about 1 to 2 milliseconds. The action potential in cardiac heart tissue will last 200 milliseconds. The contraction in skeletal muscle will be anywhere from 15 to 100 milliseconds. The contraction in heart tissue will be over 200 milliseconds. So the benefits of this longer action potential and contraction is you get a more sustained contraction. It's like the heart contracts and squeezes the blood out as opposed to just contract, right? You want to get a slower contraction and a more sustained contraction to make sure you gain the blood out of the chamber. So this is where we get to electrocardiography, and most people would recognize this, if they do recognize this, as your ECG. So some of you may have an ECG. This is where they put these leads on. So usually they're round or square, maybe about anywhere from 3 to 4 centimeters in diameter, and they're sticky. They stick them on your body cavity at different points, maybe one up by the right shoulder, one up by the left shoulder, depending on how many leads there are. If it's a 12 lead ECG, you'll have 10 of these on you. If it's just a 3 or 1 lead ECG, you'll just have 3 of these stickies on you. And what we mean by a lead is when you have one sticky tab and another sticky tab, the line between those sticky tabs, measuring the voltage difference between those sticky tabs, is 1 lead. So with 10 sticky tabs, you get 12 leads because you're using some of the sticky tabs more than once for more than 1 lead. But the ECG or electrocardiograph can detect electrical currents generated by the heart. And it's a graphic recording of the electrical activity. And really it's a composite of all action potentials at a given time, and is not just one action potential. Okay, so it's kind of like summating a bunch of action potentials in there, and you get these electrodes, those sticky tabs, which are placed at various points, on the body to measure voltage differences. Okay, 12 lead being most typical. So the features of this are, now when the general population, you say, hey, what does a heart rhythm like an ECG look like? They're like, oh, it looks like that. Well, or they draw just some kind of squiggly line. Well, it's not really what it looks like. It looks like, in actuality, what we see here. So we see that it consists of a P wave, a QRS complex, and then a T wave. So this is time, and then this is depolarization. So the P wave represents depolarization of the SA node in atria. Your QRS, sorry, complex is ventricular polarization, and hidden is atrial repolarization. Now, why is the atrial repolarization hidden? Because the ventricles are so big, when they depolarize, they hide the electrical events of atrial repolarization. The T wave is ventricular repolarization. Okay. The PR segment is a beginning of atrial excitation to the beginning of ventricular excitation. The ST segment is when the entire ventricle is depolarized, and the QT interval is the beginning of ventricular polarization through repolarization. And so that's basically all an ECG is. We're looking at the electrical nature of the heart. Now, I had said, and if you want to break it down, we'll go to this next animation, which basically shows you anything in yellow is depolarization, anything in red is repolarization. So you can see here that we start to have the SA node and the atria depolarize. That is your P wave. Then we start to see the ventricles starting to depolarize. That's your QRS, but the atria are repolarization, and it's hidden by the ventricles depolarization. Ventricles completely depolarize, and then they start to repolarize, and that's your T wave. Now I mentioned before the break that if you have issues with the heart, it's usually one of two issues, either a hydraulic issue in terms of blood or an electrical issue. But electrical issues can reflect hydraulic issues. So for example, you may perform what's called a stress test. So this is where you have either a 1 or a 12 lead ECG connected to you, and you are walking on a treadmill or pedaling on a bike, and every minute to 2 minutes, the intensity is increased. And so an ECG at rest may not reflect any issues, but as you start exercising at increasing intensities, we may see any potential issues reflected in the ECG, because as the heart requires more oxygen with an increase in exercise intensity, if there are, say, partial blockages of arteries, then that will be reflected in changes in the ECG pattern. And it takes a technician to recognize this and to identify this. And we don't get into too much clinical stuff in the course, and I'm not going to ask you, to identify these ECG patterns, but these are actual ECG tracings. And so we can see with a regular ECG pattern, you can see the P wave, QRS, and the T wave. And the things we're looking at is we're looking at regular intervals for the QRS or for the P wave. We're looking that there's no depression between the QRS and T wave. It's pretty flat. And there's nothing missing. And so basically time is represented by the x-axis, depolarization, amount of depolarization is represented by the y-axis. Now, a junctional rhythm, so the SA node is not functional, and as a result, you don't have a P wave. And now the heart's beating 40 to 60 beats per minute, which is what the AV node wants to do. So we can see there's no P wave before the QRS. A second degree heart block, so the AV node doesn't conduct some impulses from the SA node. And so as a result, there are more P waves than there are QRS waves, right? So you can see we're missing a QRS here and a QRS here, but you had a P wave right there, but no QRS afterwards. And then ventricular fibrillation is basically right what you get before you die. So ventricular fibrillation says, remember, we said that the heart wants to contract in synchronized fashion. Well, the heart's not contracting in synchronized fashion. We're getting action potentials all over the place. Like basically the heart, instead of contracting, is quivering. If it's quivering, it's not pumping blood out efficiently. If it's not pumping blood out efficiently, it's not getting blood to itself. If it's not getting blood to itself, eventually the heart will stop. So ventricular fibrillation is quite dangerous. If you have a automatic external defibrillator, an AED, this is when it will shock the heart. It will shock the heart to try to restart it. But this can be a real issue. And there are other issues, but for exam purposes, I'm not going to ask you what is this, but you do need to be aware that the ECG can pick up issues with contraction of the heart. So the mechanical events of the heart, now we've seen this before in the lab when we talked about blood pressure. And this is now where I had said before, don't worry about that top part. Now we're worried about that top part, that we see the P wave up here, the QRS, and the T wave. And so with the P wave, that's when we have that little kick, right, of the atria contracting to put the extra little bit of blood into the ventricles. The QRS occurs right before the left ventricle starts to contract, and the T wave is when the left ventricle is starting to reset itself. So remember, you need to know that systole is contraction of the heart, and diastole is relaxation. And the cardiac cycle is the heart blood flow with one complete beat. So it's basically atrial, systole, and diastole, followed by ventricular, systole, and diastole. And you need to know that the mechanical events follow electrical events that are seen in your ECG. So with ventricular filling, the pressure is low, and basically about 60 to 80% of blood passively flows from atria to ventricles through open atrioventricular valves. Atrial depolarization triggers atrial systole, P wave, and then atria contract, pushing remaining blood into ventricles. And then we have a term called end diastolic volume, or EDV, and this is basically the volume of blood in each ventricle at the end of ventricular diastole. Depolarization spreads to the ventricles, which is your QRS wave or complex. And then the atria finish contracting and return to diastole, while ventricles begin systole. So that's the start of it. And of course, we're going to take it all the way. Bum, bum, bum. So ventricular systole. Atria relax. Ventricles begin to contract, rising ventricular pressure causes closing of atrioventricular valves. And then we have two phases, which we had mentioned in the labs. We have the isovolemic, volumetric contraction phase where all valves are closed. So this is where the ventricles start to contract and just increase pressure, but not volume. So they're contracting, but the valve's not open yet. So nothing's getting pushed out. And then we have your ejection phase, ventricular pressure exceeds pressure in large arteries, forcing the semilunar, so the pulmonary and the aortic semilunar valves open. We'll go up here for number 4. Then we have isovolumetric relaxation, early diastole. Okay, so following ventricular repolarization, which is your T wave, the ventricles are relaxed. And the atria are relaxed and filling. Any backflow of blood in aorta and pulmonary trunk closes the semilunar valves. And this is what causes what's called a dicrotic notch. Brief rise in aortic pressure as blood rebounds off the closed valve. So we see this dicrotic notch right here in the green. So when the ventricles start to relax and blood wants to go back, it closes the semilunar valve, which causes that brief like back wave of pressure. And then when the atrial pressure exceeds the ventricular pressure, the atrioventricular valves open up again and the cycle begins. So it's just a matter of knowing this process and being able to walk through it properly. So in terms of heart valve disease, we're looking at the tricuspid valve here, which is on the right side of the heart. It's lower pressure. You have a bicuspid valve on the left side. But in this case, we'll talk about the tricuspid valve. So when we're talking about heart valve disease, we're talking about heart murmurs. And these are defined as abnormal heart sounds heard when blood hits obstructions. So If the heart is hitting something it shouldn't, or going through something that it shouldn't, that's when we have a heart murmur. And really with valves, there's two basic types. You can say incompetent valves, where they fail to close completely, allowing backflow of blood, and this causes swishing sound as blood regurgitates backward from ventricle to atria. So the blood's actually flowing backwards, and this can present a problem. This can actually lead to heart failure, which means the heart eventually becomes too weak to be able to pump enough blood to meet the demands of the body. There's also stenotic valve, and this is when a valve fails to open completely, restricting blood flow through the valve. Causes a high pitch sound or clicking as blood is forced through a narrow valve. And this is basic concept of whistling, right? Like I narrow my lips and put air through it, and you hear whistling. Well, same thing. You get a high pitched sound because the blood can't get through the valve properly because it's not able to open all the way properly. So it brings us to a concept that you'll need to understand in second semester, and that is cardiac output, CO. Okay, so the definition of cardiac output is the volume of blood pumped by each ventricle in 1 minute. And we're primarily concerned, especially with exercise, of cardiac output of the left ventricle. Why? Because it's pumping blood to the rest of the body. So the equation for it is cardiac output equals heart rate times stroke volume. Most people are familiar with heart rate. Heart rate is the number of beats per minute, but stroke volume is the amount of blood ejected per heartbeat. So if we take how much blood is ejected per heartbeat and multiply it by heartbeat, we get cardiac output. At rest, normal cardiac output equals 5 to 5.2525 liters per minute. And if you want a perspective on this, in North America at least, if you were to turn on a faucet in indoor plumbing, if you were to turn it on all the way, that's about 5 liters of water per minute. So that gives you an idea of how much your heart pumps out at rest. Okay. So stroke volume, right? The amount of blood that's pumped out per beat correlates with force of contraction. So if the heart contracts more forcefully, you're going to get a higher stroke volume. Maximal cardiac output. So cardiac output does go up with increasing intensity in exercise. So non-athletes, let's say this is a recreationally active person, could be anywhere from 20 to 25 liters per minute. An athlete could be 35 liters per minute. So 10 to 15 liters higher than a resting person. And then we also have cardiac reserve, and hopefully you're familiar with cardiac reserve from either fitness instructor leadership or introduction to fitness and health. But this is the difference between resting and maximal cardiac output. And cardiac reserve, cardiac output, is affected by stroke volume and heart rate, right? If heart rate goes up, cardiac output goes up. If stroke volume goes up, cardiac output goes up. If heart rate and stroke volume go up, cardiac output goes up. So mathematically, stroke volume, stroke volume is equal to N diastolic volume, how much blood is in a chamber when it's completely filled up, minus N systolic volume. Right, so N diastolic volume is basically how much is in there when it's done filling, and then systolic, how much is in there when it's done contracting. But these are also affected by other factors. N diastolic volume is affected by length of ventricular diastole, right? So how long does it have to fill? And venous pressure. If there's more pressure in the veins, you're going to fill up the chamber quicker. And systolic volume is affected by arterial blood pressure, right? So think about this. If the pressure in the aorta is higher, the heart needs to work harder to get the blood into the aorta. And force of contraction, right? If the heart can contract more forcefully, you're going to get it out there. So stroke volume is affected by three things. First off, preload. How much can we get into the chamber during that diastolic filling phase? So we can get more into the chamber during that diastolic filling phase, we're going to have higher stroke volume. Afterload. How much pressure is it pumping against? So if you have high blood pressure in your aorta, you're given everything else being equal, the heart is going to get less blood out of the chamber and into the aorta. And then entropy is basically, again, like contractility. So if we can increase how well it can contract, we can increase stroke volume and decrease end systolic volume. Most people will get confused between endostolic and end systolic. So endostolic is how much you have at the end of the filling phase, and systolic will be how much blood you have in the chamber at the end of the contraction phase. And it looks like a huge diagram again. It's like, oh my goodness, it's another one of these. But let's start at the bottom. First off, cardiac output. I'm going to see if I can move my annotation tool over here. There you go. That makes it easier. Okay, so the outcome is really cardiac output. So we're interested in cardiac output. Well, we know if we increase heart rate, you increase cardiac output. If you increase stroke volume, you increase cardiac output. So let's go up further up the chain. Well, if we decrease parasympathetic activity brings down heart rate. Or if we increase sympathetic activity, right? Sympathetic activity brings up heart rate, increase heart rate, increase stroke volume. Sympathetic and parasympathetic activities are affected by central nervous system output in response to exercise, or you've been frightened, or you're anxious, or you have decreased blood pressure. Decreased blood pressure, well, yeah, we want to keep cardiac output increased. If we increase stroke volume, well, if we increase the amount of blood going into the chamber at the end of that filling phase, we increase stroke volume. Or if we can get more blood out, we increase stroke volume. Well, to get more blood out, you could contract more forcefully, and that will decrease end systolic volume, which will increase stroke volume, which will increase cardiac pressure. But how do we increase contractility? Either the sympathetic nervous system, or you get some epinephrine, right? Adrenaline, or thyroxine, or too much calcium. If we want to increase diastolic volume, we increase venous return. So to do that, we increase ventricular filling time. So we think about this one. If you start training aerobically for an event, let's say you're running 10 kilometers an hour on a treadmill at 1% elevation. Originally, your heart rate's maybe 160 beats per minute. But after a month of training, your heart rate is down to 145 beats per minute at 10 kilometers an hour, 1% elevation. Well, because your heart is contracting less per minute, it has more time to fill. And also, if we are exercising, just the muscles contracting will cause an increased venous return. The sympathetic activity, the activity of the sympathetic nervous system will cause an increase in venous return. Or the respiratory pumps will also cause an increase in venous return. So really, we want to worry about increasing end-diastolic volume and increasing contractility, because this will also lead to the Frank-Starling law of the heart, which says if we can get more of a preload, we get like a contraction reflex. And basically got over all those things. So what are other things that would affect heart rate? I think I can move my annotation bar back here. Okay, first off, age. A baby in womb has the fastest heart rate, and it declines with age. Biological sex, right? Females in general have higher heart rates. Exercise. It will increase your heart rate during session, but in general will decrease resting heart rate and body temperature. Heart rate increases with increased body temperature. I learned how to type there. So these factors, I mean, for example, a baby in the womb will have a heart rate of about 140 to 160 beats per minute. And then as we age, it goes down. In general, biological females will have higher than biological males. We know that as a fact of increased stroke volume, athletes' resting heart rate will be lower, but of course, when you're exercising, it goes up. And body temperature, if your body temperature is increased, your heart rate goes up also. In terms of the frequency of heart rate, so we have a normal heart rate, again, about 72 beats per minute, could be lower, could be higher. Tachycardia is you have basically faster. And this is at rest. Generally, we mean at rest. I mean, if you're exercising, then, you know, of course your heart rate may be, and probably will be, greater than 100 beats per minute. But if it's at rest, that's an issue. And in fact, if you become accredited or certified to work with clients or patients, if the heart rate is higher than 100 beats per minute at rest, you probably cannot train or rehabilitate that client or patient until you've received medical clearance. Bradycardia would be basically anything slower than 60 beats per minute. And it could result in inadequate blood flow in non-athletes. Most athletes I know have a resting heart rate lower than 60 beats per minute. And it's not of concern. It's when you're not active, you're not an athlete, and it's lower, that can be a problem. And then we have a regular heart rate. And a regular heart rate, everybody actually gets a regular heart rate. Like the vast majority of the population have what we call arrhythmias, and this is where you're missing a heart rate. So in this case, we just see a missed QRS complex. In general, it's not of concern unless it becomes a very regular occurrence to the point where damage is being done. So in terms of developmental aspects of the heart, when you're a baby, 20 days after conception, the endothelial tubes begin to fuse. About 3 weeks after conception, it actually starts pumping, and it continues to bend and elongate. And by 4 weeks post-conception, after conception, is bending. Like you actually have a noticeable atrium and ventricle in there. And then by about 7 weeks after, you have the basic formation of the heart. And that's it. Now, again, we don't do a whole lot clinical, but in this case, we are doing a bit of clinical stuff. You may have different defects. So when you're in utero, you actually have what's called a fossa ovalis within the heart. It's a hole between the left and right ventricle. Why? Because you're getting your oxygenated blood from your mother. And then when you're born, the higher pressure in the left ventricle causes this to close. But 1 out of every 500 births, this may be open. You get mixing of the two, so they can go in surgery and close them. It's now relatively routine. You could have coarctation of the aorta. So part of the aorta is constricted, which means your left ventricle has to work harder. But because it takes place over time, then the heart may eventually get hypertrophic cardiomyopathy, like it gets heart failure. So you have a very young individual with heart failure. Why? Because 24 hours a day, 7 days a week, their left ventricle has to pump blood through the narrowed aorta, which is effectively raising blood pressure, effectively making the heart work harder. And then you can get what we call a tetralogy of Fallot, which is basically, we've got multiple issues here. We have the hole still open. We have the pulmonary trunk, which is which has been reversed, hypertrophied off the right ventricle, and the aorta opens from both ventricles. So this could be an issue. It's 1 out of every 2,000 births. It is rare, but it is possible. With developmental aspects in terms of aging, so regular exercise can keep the heart healthy. So one of the aspects about fitness and health promotion and our associated degree programs we could call kinesiology is we look at preventative healthcare. So we don't wait until you have the heart attack and then tell you how to get better. We say, hey, start doing this now so that you can either prevent the heart attack, delay the heart attack, or if you have the heart attack, you have a better chance of surviving it and you have better outcomes. So we know regular exercise can keep the heart healthy. And the general recommendations aren't that much really. 150 minutes of physical activity every week is a bare minimum you should be doing. That's not much. You know, you think about it, 150 minutes, that's like 2 hours, 2.5 hours. So you go for, say, a 25-minute walk 7 days a week. None. Like you should be getting, and that's if you take transit. Let's say you get off a bus stop early and walk 10 minutes to where your destination is instead of getting off right when you need to. But the vast majority of the population don't even get this. So we look at age-related changes, and we could see sclerosis and thickening of valve flaps, which leads to murmurs. Sorry, missed a C there. Right? We see a decline in cardiac reserve. Means the heart becomes less efficient. We can see fibrosis of cardiac muscle, which means it's a stiffened heart, and you may get arrhythmias caused by conduction system problems. And you can also have atherosclerosis, which can be averted by good diet and exercise. Atherosclerosis is where you get plaque buildup on the arteries. And if that plaque ruptures, you can have a heart attack, or maybe it just keeps building to the point where it's very little blood is getting through. The fibrosis, we know from research, from decades of research, that endurance trained athletes have very elastic hearts. But we also know that to a certain degree, you can train your heart, and the heart becomes more stiff as you age. So if we train the heart, it can retain some of its elasticity and efficiency. And the cardiac reserve is basically maximum heart rate decreases with age. So the equation is 220 minus your age to get your predicted max heart rate. A rough idea of predicted max heart rate. So if you're 20 years old, 220 minus your age, you have a predicted max heart rate of 200 beats per minute. If you're 50 years old, 220 minus your age, your maximum heart rate is predicted to be 170 beats per minute. So we know that the cardiac reserve is decreasing. So going back to, if you exercise, if you're regularly physically active, you can prevent or delay a lot of these bad outcomes. And if you do have, say, a bad outcome such as a heart attack, you increase the chances that you could survive the heart attack or have a better outcome and thicker recovery from the heart attack. So we are going to finish our annotation. We are going to finish our recording.